geometric sequences in series. So a geometric sequence is one that increases by a pattern, just like the arithmetic sequence did. But the amount that it goes up by, instead of being a fixed amount we're adding each time, we're multiplying instead with a geometric sequence. What we're multiplying by is the common ratio. So here, notice that 1 times 2 gives me a 2. 2 times 2 gives me a 4. 4 times 2 gives me an 8. I can get the next term in the sequence by multiplying the previous one by 2. So 2 is my common ratio. So I can find that ratio by taking any term in the sequence and dividing by the previous one. So 8 divided by 2 is 4. That's the same as if I took 32 and divided by 8, or 128 and divided by 32. Either way, it'll give me that common ratio of 4. In a geometric sequence, if the first term is a1 and the common ratio is r, then the nth term of the sequence is a1 times the ratio to the n minus first power. For example, if I want this fifth term in the sequence here, notice I need to know what I'm dividing by. So the r, I just take any term and divide by the one preceding it, and I get -3. Notice also my a1 is the first term that appears. Now, notice that I could get the next term in the sequence just by multiplying 54 by -3. Let's use our formula. A5 would be a1 -2 times the r -3 to the power n 5 minus 1. That's -2 times -3 to the fourth power. -3 to the fourth is 81, so that would be -162. When I multiply by the -2. I want to find r and a1 for the geometric sequence with the third term being 50, so that tells me a3 is 50. And the seventh term is 0.005, so a7 is 0.005. I've got to use this information to figure out the ratio. Now, notice in a3 would be a1 r squared, so that's equal to the 50. And my seventh term would be a1. A7 would be a1 times r to the 6, so that's the 0.005. So to find my r, I can take a7 and divide by a3. So a7 is a1 r to the 6. I'm dividing by a3, so a1 r to the 2. And notice that that's 0.005 divided by 50. Notice the a1s would divide off, and I'd subtract exponents here. So r to the 6 minus 2 is r to the 4th. Divide 0.005 by 50, and we get 0.0001. So to get r by itself, I'd take the fourth root of that expression. So r is 0.1. All right, now once I know my r, I can plug into either expression to find a1. So I'll plug up here into a3. So a1 times the r, which is 0.1 squared, equals 50. 0.1 squared is 0.01. That's not an equal, that's a times. And so to get a1 by itself, I divide by 0.01. So a1 is 50, let's add 2 more zeros, 5,000. So there's our answer. R is 0.1 and a1 is 5,000. Now, a geometric sequence that has the first term a1 and common ratio r, the first n terms will sum to a1 times 1 minus r to the n over 1 minus r. For example, here, if I look at this, my sequence generated by 2 to the I would be 2, 2 squared, 2 cubed, and so on. So this is telling me to add up the first 4 terms. So I would go 2 plus 2 squared plus 2 cubed plus 2 to the 4th. Well, I can just plug that into my calculator, but let's get there using the formula. Our formula has the n value of 4. A1 is the first term in the sequence, so 2. 1 minus the r, how much am I increasing by? A ratio of 2. N to the nth power, so 2 to the 4th, over 1 minus 2. So that's 2 times 1 minus 16 over negative 1. And that equals 30. And if I add up 16 plus 8 plus 4 plus 2, I get to 30. Now the infinite geometric sequence, 2, 1, 1/2, 1/4, 1/8, if I look at the sums, the first sum is just the first term, 2. My second sum is 2 plus 1, so 3. My next one is 2 plus 1 plus 1/2, so 3 plus a half is 3.5. My fourth one would add on a quarter. My next one would add an 1/8 onto that. And then I'd add a 16th onto that. And notice the more I add on, the closer this value is getting to 4. But it's not getting past 4 because what I'm adding each time is smaller and smaller and smaller. When the ratio is less than 1, the infinite geometric series is convergent and converges to A1 divided by 1 minus r. All right, here my A1 is the first term that appears, the 18. The r I find by taking any term in the sequence, 6, and dividing by the term preceding it, 18. So that's a third. So my sum is equal to the A1 over 1 minus the r. This is directly the formula from the previous slide, A1 over 1 minus r. So that's 18 over, that's 3/3 minus 1/3. So 18 divided by 2/3. So I'd flip up and multiply it and make that 18 times 3/2. So 9 times 3 is 27. So the value of that sum is 27. All right, let's do the same thing here. Now, notice that if I expand this a little, plug in I equals 1, and I'd get negative 1/3 times 3/4 to the 0. Anything to the 0th power other than 0 is a 1. Then plus negative 1/3 times 3/4 to the, I'm plugging in a 2, so 2 minus 1 is 1. And then plus negative 1/3 to the 3/4 squared, and so on. So I can see my r is 3/4. It's how much I'm going up by each term. Notice it's the item with the I minus 1 on it. I also see this is my A1, because this first term here, anything to the 0th power other than 0 is a 1. This is negative 1/3 times 1, so the first term is negative 1/3. So my infinite sequence would sum to, this is less than 1, so I know it's convergent, negative 1/3, the A1, over 1 minus 3/4, the r term. So negative 1/3 divided by 4/4 minus 3/4 is 1/4. So I would go negative 1/3 times 4 over 1. So negative 4/3 is the value of the sum. All right, let's write this sum as a rational number. Now, notice the A1 here is the first term that appears, so 0.7. Now, how do I get from here to here? R is 0.07 divided by 0.7, and so that would be a 0.1. So, all of this added up adds up to A1 over 1 minus r. So this would be A1 0.7 divided by 1 minus 1.1. So this would be 0.7 divided by 1 minus 0.1 is 0.9. So we can move the decimal over one place in the numerator and denominator and get the fraction 7/9. So this sums to 7/9.